All right, to today's lecture, I'm going to finish our last lecture about this feed-forward network, and then we'll give you some example about this recurrent network. Okay, the difference between the two structure of network is that a feed-forward network, you have a diagram. You have, let me see, the inputs that goes in one direction. Let me see where, yeah. Oops. Yeah, here from left to right. The information only goes in one way, it doesn't go back. So for recurrent network here, so this is supposed to be a neuron. It got inputs from other neurons, right? It sends out inputs to other neurons, right? So this is so the information may go in a loop, right? That's a recurrent network. As we know, in the brain, in most parts of the brain, you always see this kind of a recurrent network. But some parts of the brain is more like a feed-forward network. So this kind of network is easier to study, but this one, of course, is more powerful because it's more general. Right? So I'll give you examples of all these networks, so you have some rough idea what's the capacity of these things can do. Right? So last time we talked about this perceptron. The simplest one is just a linear combination of the inputs. You have some weights, you add it together, you get one output. That's the simplest one. For this system, we know that, you remember from last time, the system can do classification, but the decision boundary in the two dimensions for two inputs would be a straight line. So the straight line means it's all the inputs that have the same output and lie on the straight line, right? So if you have a decision boundary, that if the output is more than something, you classify into one classes. If it's less than the value, it's classified into different classes. So you cannot do classification of XOR, no matter what's your learning rule, right? It's not just learning rule; it's a representation of the system that's very limited. So multi-layer perceptrons, basically you have, if you look at each neuron here, the unit it receives inputs from a bunch of others. It's just like a simple perceptron, right? So if you look at another one, it do the same thing. So of course, each of the units with a neuron, you have a nonlinear input-output function. Right? We talked about before the different kinds, typically monotonically increasing, right? There may be a linear threshold, there are sigmoidal shapes and different shapes. So that nonlinearity turned out to be important. Right? If you don't have nonlinearity, suppose it's just a linear network. You have a 3-layer or 4-layer or 5 layers. That's not different from a single layer, because a linear transformation after nonlinear transformation, the total effect is still linear transformation. You can just use like a 2-layer network, good enough. Right? So that's, if you have nonlinearity, it pays to have multiple layers. So if you add just single layer, you call it a hidden layer, hidden in the sense that you have input and output. You cannot see it from the output directly, right? It's hidden from your view. So you can solve this XOR problem, right? So in this example, these are threshold, these are the weights. So each of the units just like a step function as a gain function. So you can just add this nonlinearity, but there are many different ways you can solve the problem. You just add some nonlinearity, you can always solve the problem like the XOR problem. Right? So this kind of network has been used like 30 years ago. It's been used in many different applications. In this case, for the pronunciation of English. So basically, the input is a bunch of words, right? You have a window, you can sliding through. There are some hidden units. You teach it. So what's the pronunciation, right? So English pronunciation turned out to be quite difficult. If you're a native speaker, you never realize how difficult it is, because lots of things are irregular. So in this case, if you want to pronounce it correctly, there are many rules figured out by linguists, right? There are exceptions to rules, and there are exceptions to exceptions. The rules are very complicated because of the history, how the English language actually constructed. It's very complicated. So in this case, I think this is an example. Right? If you do this, you have inputs, you have some hidden units, you have a bunch of weights and the threshold, you have the parameter. So in this case, you don't teach the system what the rules are. You only give them examples. So we're given some bunch of examples, say this should be pronounced in this way, right? You give a bunch of examples, you use this gradient descent we talked about last time. You try to minimize the error between your desired output and actual output, right? You change your parameter to minimize that error. So after you give enough example, you learn all the weights. So the system itself it embodies some rules, right? Even the rules never told to the system explicitly. Right? You can learn it from examples. So that's actually something interesting about this kind of system, right? So there are many different examples. So why the system is so powerful? You can learn very complex stuff, right? It's in a very interesting manner. So here's one idea, so function approximation. So the idea is that what you want to learn is some input-output mapping. It's very complicated, highly non-linear. So in general, this is just a one-dimensional example. You have, for example, a Taylor series that you have some basis function, which is like power function or polynomials, right? You combine them, try to approximate any function to arbitrary precision, right? If the function is well behaved. Or you can use Fourier series. So your basis function will be sinusoid, right? You add different sinusoid, try to approximate any function. Right? And in mathematics class, you know that if you have enough of these terms, you can approximate your function to arbitrary precision. So the neural network is sort of like that. So it has a bunch of basis functions, right? These basis functions are these sigmoidal functions. And you nest these things together, try to approximate any function. Right? So in this case, I'll give you a very intuitive explanation. So you will see intuitive. We don't prove mathematically very rigorously because that takes too much time, right? But I think the basic idea is actually quite simple. Now in this case, look at this. Suppose you have one input, so one-dimensional, just x, right? There's one output, right? Suppose you have two units. Each of the units has a sigmoidal gain function, right, that we talked about before. This is like a stereotype, like a stereotyped neuron, right? Let's suppose these two units has two different thresholds. So this red one, they have a gain function like this. Threshold is higher, so you have to be inputs larger. They can have big inputs. So the blue one have a lower threshold, all right? So suppose you have your inputs from low to high, you sweep this way, so these two neurons behave that way. Now suppose the weights from this neuron to the next step is positive, the other is negative, right? So basically you see from here, from the output the units here, it's the subtraction of G1 from G2, right? So that's from these subtraction. So if these two curves subtract, you get something look like this. It's like a bump, right? So you can imagine if I use very narrow, very high, like a high slope, it's very steep. This function will look like what we call a box function, right? It's different from two-step function. I can make it very narrow. If the threshold of the two units is very close to each other, I can make it very narrow, right? That can be done, right? So now suppose I have a bunch of units, many hidden units, right? I just add them together in this way to approximate any arbitrary function. You can see that for this pair, I can make this pair to behave like a box function. It doesn't care, it doesn't respond to anything else except only when your input is in this very narrow range. It gives some output, right? Then you can break up your function to many of these like boxes or little stripes. You can approximate the function to arbitrary precision you want, right? This is a very intuitive explanation. Actually, this means the exact shape of this gain function actually doesn't matter. You can see, right? There are many different types. You can put them narrow enough. It's like a Dirac delta function, right? You can approximate any function if you want. So in answer, you would say, okay, if that's the case, would I just like a 3 layers of neuron, would that be enough to approximate any function? Why do you have so many layers in the brain? The brain is complicated. Well, here, this is why. So there's one theorem about this structure functional three-dimensional multi-layer perceptron. So basically the idea is that, so suppose you consider input-output function of a multi-layer perceptron, so many different layers, right? The idea is that suppose you have two different networks. maybe one neck have more layers than the other. So maybe there's 3 layers, the other maybe 5 layers. Is there a question there? Yeah.
I'm just wondering, on the previous slide, with the G1 minus G2, how does that relate? Like, what is that in a physiological context? What are we relating?
Oh, so relate would be that this is like 2 neurons. Right. So the G function would be input-output function. Means you give a current inject into a neuron, they have a firing rate, right? There's the threshold. If there's also like a saturation. You cannot go any further. There's a maximum firing rate. It cannot be over that. So that's sort of biological. So the plus minus would be this blue cell is the excitatory cell. This cell is inhibitory cell. You add up their output, right? In the next step. So this like physiologically is very simple. All right. So here they say that if you have two network. If any of the parameters are different, for example, number of layers, or how many neurons each layer, so what's the connection weight, right, among any neuron between the 2 layers, between any of the 2 layers, right? So the idea is that, so this is proof, this by Pfefferman is actually, it's a real mathematician. It got a Fields medal. It's a real mathematician. It proves that for this kind of network, you use a sigmoidal, standard sigmoidal gain functions. If there are 2 networks, if any of the parameter is different, for example, one network has 1 more layer than others, right? Maybe one network has just 1 more new neuron than others, or maybe it's just one of the connection weights is different. If anything is just different, the input-output relationship of 2 networks cannot be exactly identical. It can be very close. We say we can each 3 layer can approximate any function, but there are small differences, right? And they can never be really identical, except for in a very trivial case. For example, one neuron never used anywhere. The weights, they have no output whatsoever, right? In that case, or maybe 2 neurons, they work almost identical twins. You can merge them. You can split them in different ways. So that for these trivial cases, basically the structure and the function has a unique relationship, right? So in other words, it means I can have maybe really a 4-layer network. You can use 3-layer network to approximate me, but that's not exactly correct, right? And another problem is generalization. So if I give you a few examples, for example, this is a dog, this is a cat. For small kids, I give you a few examples, you already figured out. I give you another one, immediately you got the idea, right? It's not say, but it's different from like a Google approach. Google or any machine learning, typically you have a huge amount of data. Basically, you have already seen pretty much all the cases. You gave me a new example, it already has something in your example already very close. Right? The learning is not right. It's different from the real brain. Brain is much smarter. So that means if you have this function, suppose a function like this, you don't break up and only learn the little piece like this. This is like a lookup table. You just remember each individual cases. Right? You learn from here. It doesn't generalize. It doesn't tell you anything about things that are far away. Right? It cannot generalize. All right. There's just some like a summary of this learnings. All the parameters learned by weights. The learning rule is more complicated, and a standard method called the back propagation of error. So the back propagation is just exactly the same as the gradient descent method we talked about before for simple perceptron, except there are many different layers. When you do the chain rule to do the derivative, it looks like the error propagating mathematically. But that's not biologically plausible. I don't think biology uses that kind of a learning rule. But so the back propagation even is still used still used today, right? But that's a simple gradient descent algorithm. All right. I just mentioned some example. I'm not going to go detail about this perceptron. I want to talk to you more about this recurrent network because there's something really interesting. So there are some advances. One is with support vector machine, right? So in that case, they only look at the last layer, right? This, whatever done before, you don't go into detail. Just say there's some function, nonlinear function that include whatever done before. Then you combine things linearly. So for perceptron, you can separate 2 different classes with a straight line. In a support vector machine, you separate them. For example, these data set are identical, but you can want to separate with maximum margin, right? The hyperplane, so that you are for the example, at the border, you are very far away rather than just so close by. So give you a better, like it's a more robust. So the method based on linear programming, I don't think it's biologically plausible, but that's the method people typically use. But you can see this thing is really grow out of this perceptron. Right? It's the next step. It's better. Another is called a deep network. This is basically a multi-layer perceptron. Instead of a 3-layer, you have many, many layers. People use 10, some over 100 layers, so you can do all sorts of things. But this network actually very interesting. You see, they borrow some concept from biology, not exactly, but just like say, each neuron combines information from many other neurons. The neuron has a nonlinear transformation, the input-output relationship, just those very simple ideas. And this network, recently they did a lot of good work, right? In many competitions, they win a lot of competition. So it's surprisingly powerful. All right. Recurrent network. Recurrent network are also interesting because it has inherent dynamics, right? And not just give input, there's output, right? So as we said, this way is the neuron, the inputs, it may go to cell, go to other neurons, right? Potentially anyone can be connected with everyone. So one very famous recurrent network is called the half-wave network. It's almost like it's over 30 years old, right? It's very simple, but it's very interesting. It's proposed based on analogy to in physics, called the Ising model of the magnetic materials, right? So a simple network looks like this. So you have a bunch of units. Its states is described by UI, all right? So you're familiar with the equation now, right? There's a derivative, there's a decay term, right? So this sum is the effect of connectivity. From all other units, the connection weights Wij, so by the convention, this means the synaptic input received by units I from J. Right? Usually you say from I to J, no, it's from J to I. Right? People typically use this way. So this means that you sum over all other units from J to the input to I. All right. So this S is a firing rate, it's output. To give it a state, you may think of it as a membrane potential U. You go through the gain function G, the sigmoidal shift, right? You get this firing rate. So the firing rates, they depend on the connection weights. You sum over. That's all. This is like a perceptron, right? You sum it over to the unit. But the unit itself satisfies this is a dynamic law like this, right? All right. So when this system reaches equilibrium state, so the time derivative becomes 0, right? Then you can say this U just equal to this sum. Right? This will look like a perceptron, right? for the equilibrium state. So this is a continuous half-wave network. Like here, you have a continuous dynamic. You can use it like a discrete. You can just say that the time step, you advance by 1. You sum over all the outputs, and you go to gain function, you go to the next step, right? Just iteratively. So when this thing reaches the equilibrium state, it's the same as this, right? Because it satisfies the same equation. So it doesn't change the equilibrium states, right? But the dynamics is different. It's a discrete. So how does system work? System works this way. System that reminds you of this auto-associative memory, sort of similar to that, but except for this have dynamics. So the idea is that you embed, you can store a bunch of memory states in a connection patterns, right, in a network. Once that's stored, the system behaves this way. So you start for some initial states. So here, each pixel corresponds to states of one neuron, one units. So black means here maybe the active, white means not active, all right? So you start from some initial state. And here the state that it's very close to one embedded, it's a spider, it's one embedded memory pattern, all right? Except for this very lot of noise stored in there, all right? So based on what you have done in your homework for the auto-associative memory, if you have a pattern like this, it resembles something stored, your output you will expect to be similar to something you already stored, right? But except for here, this is a, I wonder, have anyone tried, when you get some output in your auto-associative network that's feed forward, right? You get the output. Output is it cleans up the noise, but not exactly. There's still some imperfection. Have you ever tried to use output? You go back to network again as the input to try again to iteratively. Have you tried that? Yeah. If you iterate, the noise will be will be cleaned up even better. Right? So this is sort of it's a recurrent network. You do this automatically. You don't need to do it iteratively. So eventually you stabilize the state. Right? If you start with this is the same network that embedded many states, right? You show this image, it recovered what is actually missing, right? You show piece, it recovered the whole image. It's very similar to that auto-assertion network, except for this works have a continuous dynamics, right? It works spontaneously. So the fully connected. So basically, the idea is that what is memory, right? So this suggests that the memory, each memory pattern is a stable state of a dynamical system. Right? So the multiple memory stored in the same network. In the past, philosophically, you think that's kind of very tricky, right? So the brain can remember many things superimposed on the same hardware. How is that possible? Right, this is you can really store many things on the same network superimposed, but you can recover each one of them separately. You can retrieve from partial queue. They call content addressable association memory is some other people's word. That means I give you part of the content, you can recover the whole thing, right? Just like in the brain, you can say, oh, there's some person, oh, I forgot his name, but he played some movie and some, oh yeah, you got that. You give me partial cue, you can recover other things. So as here, it's very interesting. So it's robust against the noise and damages. So if you, for example, you cut the connection, you can cut like 50% of all the connections randomly. So that's guaranteed not to work. If any of the computer, if I cut 50% of the wire of a computer, do you think it's still going to work? Of course not, right? But this system, you can cut 50%, something 80%, 90%. You can cut a lot of the connection. The system can recover your store state with a single error. It's 100% correct. It's not just approximately correct. It can be 100% correct. And it's actually turned out to be easy to learn. It's just called one-shot habit learning. You can learn the new pattern very easily and add it on top of the old stuff you already stored. How can that be done, right? The learning rule is actually very simple. Suppose you have one memory pattern here. I just say that it's a list of states, right? Either positive, or either it's quiet, either it's excited or not excited, just plus or minus one. Just say that. And then the connection weights is just a product of this from J to I, right? Is a product of the desire of the stable state of I and J, and it's Si times Sj, right? That means if the two states are of the same sign, or either active or not active together, this weight is positive 1, right? If they're different, a negative 1. That's it. If you do this, this memory pattern will be a stable state of the system, right? So if you want to add more, so this idea is called the Hab rule, in the sense that the Hab, I'm going to talk about learning rule in a different lecture, but the basic idea is that you change the connection between two different units when both of them are active at the same time. So if they fire together, they should wire together. That's the word. So if the two units wire together, so the simple mathematical expression is the product of the activity of the two units, right? So the idea is that each of the units can be maybe 0 and 1. It's just like representing their active or not active, all right? So the product means you change the weight only when both of them are not 0. So both of them are active. Only when that case, you make the connection stronger. All right, so the rule we have is not exactly the same because we can be plus minus. So that's more like this kind of modified Hab rule. So it's not just positive or negative, but it's positive or negative compared with your average activity in the past, right? So this can be positive or negative. So I'm going to talk about learning rule in the future, but here it just gives a rough motivation. This have a learning rule like this. It is sort of related to the biology, all right? So if you want to store many patterns, so not just only this one, but you want to store a second one, like say S prime, you do the same thing. This same product, you just add them together, all right? So if you already store the second one, the first one, second one, you add the third one, you just add the product like that. So you can add many, many different patterns. It's very easy, right? All right, so So the system works if all the patterns are statistically independent of each other, as if you draw a random pattern from independent random distribution. In that case, they don't interfere with each other, for a reason I'm going to explain. So okay, this is just say the way to write it as in like a matrix form. So you take each pattern that you store as a vector, all right? Then you put each of the put the column together as a big matrix. And the weight matrix is dot product, and the product like this. This it's outer product. You sum over, divide the number of units you have. So this is equal to this matrix X times its transpose. It's the actual equivalent. All right. So that you observe, this matrix always symmetric. Of course, each of the terms is the product I and J. The product you can switch them; it doesn't change anything. So the matrix is symmetric. It turns out that's guarantees the stability of the system. All right. So this a labeled optional material means that I'm just going to talk about it. It's not going to be in your homework, not going to be in the exams. All right. So it means if you want to do like but because here you assume the standard Hopfinger network, excitatory, inhibitory units, you have equal probability. Basically, you have half the units active, half the units quiet. But in reality, in the brain, most neurons are quiet. Only a few are very active, right? Very like small percentage actually active. So if I have a pattern like that, they call sparse patterns or correlated pattern. Let's say the different picture, they're not completely independent of each other. Maybe they're sort of like a horse, only the legs slightly different, otherwise very similar. If you do that, you have interferences. The right way to do the weights is do this pseudo-inverse method, just exactly the same as you showed it before, like this, right? You know this solution is like that, right? So you do exactly this kind of weights. So this, in a special case when things are independent, it's a special case of pseudo-inverse, the transpose. This is optional for people who care about this. All right. Yeah, this want to show that how the system works, all right? So the idea is this, all right? So you see this term, this weighted sum of the inputs, the state, right? If I suppose you're already in that memory state, you go through all the connections. The total input to unit I should be equal to whatever I already stored, right? If that's the case, that means this is self-reinforcing. The system will stay there, right? So that means this is stable. It's the equilibrium state. So the mathematical means that this is an eigenfunction, right? This is the eigenvector of the weight matrix. So each memory is the eigenstate of your connection weight matrix. All right. So that means if someone, say, discovers some guy's brain, if you can measure this connectivity structure, if the system is wired up the same way, if you can measure the connection matrix, even as the person is dead, you just say, measure the connection matrix. Okay, now you have mathematical algorithms say, what are the eigenvectors of this matrix? So all the pattern would be all the memory stored there, right? You can completely recover. But in reality, maybe it's not stored this way, but this is the one very interesting model, right? Maybe I go through a little bit of the math. So it's very easy to see why that's the case. I mean, that's basically the different memory states. Suppose that it's different memories. I use superscript m and k, so two different memory states. Suppose they are independent of each other. So each of the memory pattern state Si and Sa is equal to +1, -1 with equal probability. All right. If that's the case, if I'm correlated, if you do this, the result is a Kronecker delta function, right? If it's the same memory, the product is always 1, you get 1. Otherwise, because they are random, they're plus minus with equal probability. On average, you divide by n, it's approximately equal to 0. Right? Because the different pattern are approximately orthogonal. If you use pseudo-inverse, that's different, but the idea is very similar. You prove the mathematical differently. All right. So here is to say when they're equal to 1, when they are two matter not equal, you get plus minus 1, right? They're n term plus minus 1. I want to say here, I just want to point out that this, if you add up plus minus 1 with equal probability with n terms, you get a random variable. The random variable, the size of the random variable is approximately the square root of n. Right? So this is a very typical like argument people use a lot of times. So when you n is large, this one person is equal to 0, right? So because of that, you can test that if you take a state already stored there, do all the stuff, all the orthogonal states they become 0. Only the same thing remain. You go back to the same states. So I think I want to show you why this is the case, or why you add up plus 1 and 1 with n terms, the size plus is approximately square root of n. So here's the argument. I'm not sure you have seen something like this before. So this is like a random walk model. So this is a time step. So each time you start from 0, each time you start, you either plus 1 or minus 1. It's like a stock market. Every day you go up or down. Now here with equal probability, all right? So you follow this red line. Sometimes go up, sometimes goes down. But as time goes on average, you're going away from 0, right? So this is at any given time, the cumulative sum of all these variables is a random variable. So on average, it's equal to 0, as you can see here. But its standard deviation is same as square root of n. Right? You have more steps, the standard deviation is going to be wider and wider, right? So to prove this is very easy. So this sum is a bunch of variables xi, it's plus 1 minus 1, right? You consider its square. So on average, of course, equal to 0. The bunch of random variables where each is 0, on average, over many, many trials should be 0, right? If you consider its square, it's different. You have a n plus this product term. So if you have average over many trials, this plus 1 minus 1 on average is 0, right? You depend on each other, what you get is n. So that's a standard deviation square root of n. Well, that's an argument, all right. Yeah. So each state is a stationary state. All right, so that's what we talked about before. Yeah, here's one peculiar property for this system. Right? If the complementary state, that means if you see the picture like a black and white, if you flip the sign, all right, make that black pixel become white become black. Just switch the black and white. The system is still stable. The reason is that suppose this stationary state, right, the times weight equal to itself. If you have a minus sign here, it's minus sign that carries here, right? That's mathematically equivalent. I mean, if the plus minus 1 minus is a flip, it's also stationary. So this already shows that the system can store some things not you intend to store. You usually try to store some pattern. Actually, the negative, like a photo negative of that pattern, also stored automatically. All right. So here, this example is similar to the homework. Have you seen homework already uploaded today? I think this is one of the homework is that you store a bunch of patterns like this, random patterns. This is a lockless monster. So photo, you know. So if you start with random states, the system will eventually settle into some, typically one over the states you actually store. All right. But sometimes you get some state look like this. You see, it is not one of the things you store. It's like a mixture of things you store, right? So you know, people like try to imagine there's an animal. The head look like an eagle, right? The body look like a lion or something. You know, that's kind of mixed together. So this system, if you store this bunch of patterns, it's very easy to get some states look like this. It's like a mixture of two different things here, right? It's not just linear combination. It's a kind of part. It's kind of combined in a very interesting way. So these could the spurious memory states. So in your homework, you can play with the system. You can see for yourself. But these systems are not very stable in the sense that if you make a perturbation of a system, just like if you add a bunch of noise, it will go back to the same system. If you add some noise to some state like this, it will disappear and go to something else. So it's not that stable, right? So the stable state is still the one you already store, but the system also have this kind of a spurious state. I just want to mention this some interesting property of this kind of system. All right, optional material, crosstalk, interference of different patterns. So now you wonder if you want to store a new pattern to a system already there, you just do that Hab rule, that product, just add more, right? To add your connection weight on top of stuff you already have, you just have a small increment. So the question is, will your new memory interfere with things you already store? The answer, of course, is no, if they are independent of each other. The one problem is that, well, this is true if you don't have store too many memory patterns, all right? It turns out equals to memory load. It's a number of memory M divided by the number of neurons in the network. This is called the memory load. It's about 14% of maximum in the half-field network. If you store too many, nominal state will be stable. It will like a phase transition. Eventually, the system will not working anymore. All right. So you say, why is that this ratio is important? So this optional material, right? I just go through it for people who want to hear, right? Otherwise, don't worry about this. All right. So the idea is this: so if you suppose you have a connection weights here, all right? I just want to explain the idea. So why is that this ratio is important? So suppose you have a bunch of memory already stored. You have the states. So this weights is here is this memory, the rule we talked about before. Then you can split it up, all right, into the state that's exactly correct with all the cross-talk terms. So this sk with any m that's not equal to k. If you add this term, you realize these terms are also like a +1 minus terms, right? But it depends because the sum is sum over not only number of units and also number of memory you have, because the connection weights is sum over all the memory. So because of that, so this plus minus term is the square root of n times m. Well, there's -1. If you go through this, it depends on the number of memory and memory state. So you compare this size. So basically, you have a system that you recover the correct state, plus you have a noise term, all right? So the noise term, you see, there's n here, but the total result is m -1 divided by n, right? So that means